Well, my computer crashed yesterday, so all the work put into the slides is gone, and instead I will have one line per minute on the blackboard. First of all, thanks to the organizer for allowing sheep and wolf's clothes in their fold. I'm very sympathetic to the formal theorem proving, and at the same time very critical because I'm a mathematician, and we mathematicians think somewhat different about formal things than computer scientists. But Shankar put in his opening lecture, the goal of the INIBIC proof program is to define the future direction of proof technology so that it is used by mathematicians. So I want to communicate what it means for me, that I can use something. And today it's a philosophical talk. On Wednesday I'll tell about what we in Vienna did towards implementing things that bridges one half of the way towards the formal theorem proven community in the hope that they will bridge the other way, the other half. Okay. My talk is on 3 pieces. One on subjective and objective knowledge, one on what is mathematics, and one of mathematics as a dynamic language, where the third part I don't know whether I will come to it. It's just if there's enough time, it's difficult to predict. So I need some things to write on the blackboard. So, I'm a Christian at heart, but even those among you who are atheists will probably realize easily that God is a mathematician. Maybe the first one who formulated it explicitly was Galileo, who said the book of nature is written in the language of mathematics, and as a Christian we believe that the book of nature is authored by God. So let's go back to the creation. In Genesis 1 it says, and God said, let there be light, and there was light. God saw that the light was good, and he separated the light from the darkness. God called the light day, and the darkness he called night. Compare this to, let H be a Hilbert space. We call the Hilbert space a state space. It will play a very important role in the following. Completely analogous. God creates context, language, and value judgment. And I want to convey today that this is what mathematics is about. In the second chapter, says, then the Lord God formed man of dust from the ground and breathed into his nostrils the breath of life, and man became a living being. Then the Lord God took the man and put him into the Garden of Eden to cultivate it and keep it. So, he creates hardware, software, and purpose. Again, this is part of doing mathematics on a computer. So, and clearly, God believes in strong AI, which is the idea that everything we humans can do can be done by something created, and we are in the process of doing this for mathematics. So excuse me that I regard you as 25 theorem provers embodied in unique hardware, each of them, each with a slightly different operating system that was created in a roughly similar biological hardware by exposing it to machine learning in the form of being exposed to mathematical curricula or computer science curricula of different forms. And I believe this analogy is not so different from what we would have if a theorem prover like Isabel would be used in isolation by different groups of people for some time, trained on different components of material. It will produce many different dialects of the same thing, unless there is a whole community that makes sure that everything is matched to be identical in each of the implementations of the same system. Okay. I want to distinguish between two kinds of intelligence, namely borrowed and intrinsic intelligence. And I believe this is the main difference between current theorem provers and you as theorem provers. You have intrinsic intelligence. The software we have today is borrowed intelligence. Borrowed intelligence means all the intelligence resides in the software that was created by humans. Without that, there would be nothing. Intrinsic intelligence means you have the intelligence to build up your own internal system for understanding mathematics. You read a textbook. In the beginning, you know nothing about the subject matter. At the end, you know everything. Isabel has to be fed the textbook by some human who does a lot of work to achieve this end. There's a difference between the individual mathematician, the individual textbook, and the community of mathematicians. Every textbook contains errors. I have seen a single one which is true in the sense of formal theorem proving. Every mathematician makes mistakes, even big blunders. Nevertheless, what is known is something steadily progressing, improving, and becoming more and more perfect and more and more comprehensive. And this shows that there is a slight difference between mathematics as perceived by the theorem proving community and mathematics as perceived by the mathematics community. And the main difference is that there are many subject levels, in the sense that I will make precise in a moment, but only one object level for mathematics. The object level, that's what is communicable. That's what the mathematicians have in common. The subject level, that's the individual implementation. And we have 25 of these in this room. These subject levels are very, very different. Because of lack of transparencies, I have to get the quotes from the right places. Okay, so let's do it. So just, what are your real numbers? For some of them it's Dedekind cuts, for some of them it's infinitesimal expansions, for some of them it's equivalence classes of Cauchy sequences, for some of them it's expressions you can write down. Very, very different. But on the object level, we agree on having the same concept of real numbers, no matter how it is implemented. Hall and Isabel and Koch have very different notions of real numbers, but the theory, that is what is mathematics, should be exactly the same. It should be independent of foundations. Now the title of this is the communication of mathematics. That's what happens between different subject levels. It's what happens between Isabel and an Isabel user who has its own subject level. It's what happens between Tom Heiders and myself when we talk about the Young-Mills contractor. It's what happens between any two embodiments of mathematics or computer science. Why does communication work? It works because it's we know that we have understood someone else if it makes sense in our subject, in our subjective representation of whatever there is. Usually it makes sense. So two people meet, they start talking, and suddenly one of them thinks, well, I don't understand him quite correctly because what he or she is saying is not does not make sense to me, and that's what we perceive as misunderstanding. And then we talk about it and we figure out we took the same concept. Well, we took different things from the same concept and used the same word for it. So, this problem was, to my knowledge, first described by Platon in his dialogue on Hippias. It's the birth of the notion of a precise concept. So Socrates dissects the language of his victim Hippias into scrapings and shovings of discourse divided into bits, with little pieces of disconnected nonsense, in order to find out what precisely is agreed upon. Occasional deadlocks are where Hippias says, I cannot agree with you, Socrates, in that, after a lot of discourse. And then Socrates, nor I with myself, Hippias. But that appears at the moment to be the inevitable result of our argument. It's the conflict between logic and intuitive expectation of meaning. And this conflict is put by Socrates to good use, because at the end, the concepts in each of the dialogues are much more clear than at the beginning. And that's what he teaches in the dialogues, to make your concepts precise, so that misunderstanding is less likely and that logic will be able to produce good answers. Next point is that the mathematics is inherently ambiguous. Which is one way to phrase Gödel's incompleteness theorem. It means you will never know exactly what is true, because some truths are undecidable. There are different models in which some things are true, and the same thing is not true, no matter how precise you make your language. Well, as soon as there is a certain complexity, our piano axioms are enough, then there is an inherent ambiguity, which is impossible to eliminate, because that's a theorem. So one has to live with ambiguity, and mathematics lives with this ambiguity very well. So let me quote Bourbaki. We believe that mathematics is destined to survive, and that the essential parts of this majestic edifice will never collapse as a result of the sudden appearance of a contradiction. But we cannot pretend that this opinion rests on anything more than experience. That's Bourbaki, who from the mathematical point of view is sort of the pinnacle of formality. Nobody has been as formal as they since then, and nobody tries. If there is a contradiction, it's based on misunderstanding, and people have to put in some effort to clarify a little bit of logic, or a little bit of conceptual foundations, until they have found the way out, and a more precise way of stating the same thing, so that all the mathematics that has been done remains safe, and only this little bug is fixed. So, this means that foundations of mathematics are not like the foundations of a building, which crashes if its foundations are found defective, but it's rather like the roots of a tree, which grow and get improved and refined as the tree grows.
Can I comment? It's widely thought that Frege's work was destroyed by Russell's paradox, and I think not noticed until a century later that Frege had never used this axiom of his in its full power, and that in fact there was nothing in Frege's development had to be sacrificed if you replaced his axioms by a weaker set.
Yes, there is also that piano, and also something that in superficially looked like being contradicted by Russell's antinomy. My brother is a historian and is in the process of writing a book on universal logic, which is about the history of logic until Peano, and he reconstructed from a modern point of view a consistent class theory as Peano seems to have had in mind. Of course, there are certain amendment steps which are difficult to justify, but they seem to have been his thinking, and you can almost preserve everything of his stuff and get something that is roughly equivalent to set of C if you consider one of the levels as classes and everything below as sets. Okay. Next point is that mathematicians generalize from single examples and not by deep learning. That's another difference between borrowed and intrinsic intelligence. That's a good graduate student. One example and suddenly, wow, it's clear that it must be this way. Why does it work? Because the semantics is very highly constrained. In mathematics, truth is simple and extremely constrained. That's why different people, even with the different notions of real numbers, and even if they know the real numbers only from high school, can agree on many things, because it just you need very, very little to agree. And if things agree, you know that you agreed, it makes sense, and that's why a single example is enough to learn. Now, if you look at a particular example and see what makes things click, you find that three things are relevant: types, grammars, and semantics. In computer science, these are three essentially disjoint research fields. In mathematics, they have to go together. Because if you skip one of them, you lose a lot of the power that makes mathematicians work efficient. And that's my talk on Wednesday at 11, where I show how to implement things based on this.
Can you say a little more about the connection between 10 and 11?
No, it's unconnected. So it's, well, it's loosely connected. If I have a single example, how do you understand it? You understand it because there are only a few possibilities to make sense of it. In fact, only one in the most interesting cases. But why is this so? The typing makes sure that very little compatibility is. If you get a type wrong, you get everything wrong. the grammar, and I will explain some of this in the next part. That's what builds up the context. While you are reading something, your mind changes. In fact, your language changes. You introduce new words, new concepts, new notation, new syntax. You introduce everything that is built up in the textbook. And the semantics is of course needed, because if you have only grammar, you get a meaningless syntax tree from which you cannot make deductions. And I have a whole hour on Wednesday to show what this means on a very formal and concrete level. And it's much of it is implemented, so it's not something that's just speculation. Okay. That was the first part. And please give me a sign 2 or 3 minutes before I need to stop, because I have endless stories to tell.
So you can, yeah, if you want, you can take another 10 minutes, maybe.
Okay.
10 or 15 minutes.
Okay. So. So there are many definitions of mathematics, none of which is close to what I believe mathematics is. Mathematics is the art and science of precise concepts and their relations. That's the most general thing. I started off as a pure mathematician, then became an applied mathematician, then did a lot of work in theoretical physics and in chemistry, and everywhere what mathematics is perceived a little bit different. But this is what they all have in common. And this is the essence. That's what makes mathematics mathematics. I'm pulling some things from the first part. It's a dynamic language. Independent of foundations. Creating context, language, value judgment. Dynamic means the language changes as you read a book or a journal article. Independent of foundations means it doesn't matter which view of the reals you have, or which view of a set or of a proposition you have. And it creates context, because each time you say let something, you put something into existence, and it exists from now until you say contradiction, and at that time you erase everything, and you go back and have a little bit insight on the previous context. Language and value judgment. Well, from value judgment you have less in most of mathematics, but at least you have a difference between a lemma, which is not the same as a theorem, except if it is a very famous lemma, like the lemma of Farkas in optimization, or the lemma of Zorn, which is an axiom. Okay. theorem is something important, it has a value judgment. A lemma is something auxiliary. And for Zorn, the lemma of Zorn was just a step in some interesting argument, and later it was put into the forefront and turned into an axiom because people noticed that this is something very, very useful. Well, or it's proved from the axiom of choice, and then it's a theorem, although it's still called a lemma for historical reasons. Okay. That's another difference to former proofs. What a textbook and a journal article does, it communicates claims, not truths. It's up to the reader to verify the claims, to believe them, to trust them, to reject them, to find counterexamples. It's not the objective of the textbook. The objective of the textbook is to claim things and to make a story that is interesting, that is challenging, and actually to make good students. This is necessary because if you justify everything, the student will become a parrot and not a thinker, not an independent mathematician.
Sorry, don't you also mean that it's necessary in general because it's impossible to communicate the truth? Or do you mean that?
I don't believe it's impossible because of this point 8.
So
it's possible to communicate the object level part of mathematics. Well, that's what real mathematics is. You communicate a lot by making claims. Sometimes you communicate even false things, but it's still. But usually you want to communicate truth. So I don't think it's impossible, but it's not provable because there will always be trust somewhere. You can move the trust to this or that, but ultimately you always need to trust. Without trust there is nothing, no certainty. Okay. So the formal theorem community complains that lots of mathematics consists of gaps because something is stated as trivial or obvious or as one easily sees or as it is well known. Now what does this mean? It means the target system is expected to take the argument either on trust or verify it oneself. So if you consider yourself as theorem provers or as learners, when talks are given on mathematics, you are like that. You take many things on trust because you believe you can verify it later, or you believe it doesn't matter so much, or you verify it in your head quickly while the person is speaking, or you ask a question, why is this so, because I don't believe it, and you get extra explanations, or you get, maybe there was a little gap. So, for a sledgehammer, much more is trivial. Than for a first order logic proof verifier, which expects that only the steps that are justified by an axiom are trivial. Okay, and as a consequence of all this, formal statements, which means claims, formal claims in this sense, are much more important than formal proofs. Of course, we would like to have formal proofs, but this is the real reason why mathematicians are currently so little interested in formal theorem proving. Because they have their own sledgehammer in their mind that tells them what to trust and what to check and how to check it. And so they want to use a formal sledgehammer only if it is easy for them. If it takes less effort to use the sledgehammer than to do the checking oneself. So, formal statements, that's a generalization of what Tom Hales wants to do with formal abstracts. He wants to do it for the major theorems in the proof. But a formal statement is everything in the textbook, if it is carefully formulated, except for the introductory pieces which are just illustrations or cultural context or so, which is not really mathematics. Okay, so let me stop with two very useful applications. That do not yet they need formal statements, but not formal proofs. Although formal proofs is a nice add-on if it comes cheap enough. But formal statement is essential to do these two things. One of them is an intelligent LaTeX editor whom we can ask to do things like well, it should be able to do whatever we can tell a graduate student to improve in his draft of a paper in order to make it of publishing quality. Because the draft of the paper is supposed to contain already all results in some form and be essentially correct, but it's poor quality. And the advisor's job is to raise it to as high possible of standard of communication. So for example, we should be able to give commands or suggestions how the manuscript should change in a way close to the directives we give to secretaries or graduate students. For example, adapt the notation of this paper to that of the other paper. Or find in a mathematical text all variable names denoting integers, then replace each one consistently by the smallest of I, J, K, L, M, N. That in context does not result in a name conflict, and that consistently names similar uses in a similar way. This is something a mathematical document should satisfy if it is of high quality. It's difficult to achieve, and at least I know from my own experience that I would pay a lot for such an intelligent LaTeX editor if one were in existence, because I'm doing lots of changes in my documents, which sometimes take 2 years or 3 years to be finished, and so it would be a big help if I could ask such questions. And the second is automatic translations of textbooks. If I have a textbook in German and want to translate it into English, you need a mathematician to do it. But if you have everything expressed in terms of a formal statement, you only need a computer science to do it, a scientist to do it, because you only need a dictionary of comparable phrases, and you can do take all the formal stuff and express it in a new language. And once this dictionary is set up once, and some software for interpreting these formal statements, then you get the translations completely automatic, not only for one textbook, but for thousands. Thank you.
Any questions? Yeah, Cesare.
I have more comments than questions. So you've been writing this in, as I understood, in contraposition to formal proofs and formal methods in general.
Complementing, I would say.
Okay, complementing, but even that. So it strikes me that point number 1 and number 2
Yes?
could be used as a definition of a formal logic. Just replace mathematics by logic, and it reads exactly the same to me.
Yes, logic is part of mathematics for mathematicians.
Precise concepts, and, I mean formal logic.
Yes.
So I don't see so much of a difference there.
There are similarities and there are differences.
Wait, are you saying about 2?
Yes, it's a dynamic.
No, I don't agree at all. Mathematics is independent of foundations, but I don't think logic can be independent of foundations.
And he explained foundations in terms of semantics. Right? When you give a formal system defined by calculus, then in a sense it is independent from the semantics. Right?
Well, it depends on what you mean by logic. I think logic is more than a formal system.
It is a formal system.
So I think
You define
semantics
a formal
and
system and asemantics.
is very integrated in mathematics. You cannot talk about mathematics without semantics.
But
You
that's
even
the
cannot
same.
do formal logic without semantics.
Right, but so I'm saying if I have to take your words for it, right, you said
Yes.
independent of foundations. What
Yes.
did you mean by that?
It means that in Holland, in Isabel and in Koch, you can do the same things on the mathematical level, although although it means in terms of implementation, it means something completely different.
It also means that people like Newton and Euler and so on and Gauss were doing mathematics long before anyone even had this idea of foundations, and that people had in their minds things that we know to be inconsistent, and yet continued. The mathematics survived.
Mm-hmm. Oh, but because it was set up as a formal systems of assumptions and ways to derive
But it
conclusions
wasn't.
for these
It
assumptions.
wasn't. Formal mathematics started around 1810 or so with Cauchy and things like that, who were sort of fed up with.
Well, Aristotle has a other opinion about that.
Well, formal logic, but not mathematics.
You mean at a level of abstraction, independent of at a level of reasoning at a level of abstraction, where
Yes.
you can forget about the exact foundation.
Yes. And in fact, good mathematical concepts are always at a fairly abstract level. They almost never make reference to ZFC. Although this is sort of the lip service that mathematicians usually pay towards foundation. Everything could be done in ZFC if one would want to do it, but nobody wants to do it because the thinking is on a very high and abstract level where you assume the properties that you need in your particular context and where you argue with these properties only. Of course, you need classical logic to do the argumentation, but it's you don't need that all the concepts you are using are actually grounded in some specific foundation.
I think in that sense, number 10 you have is extremely important. Namely, semantics is very highly constrained.
Yes.
That is it's because of that the mathematics was possible before people started getting more foundations.
Yes, yes. As soon as you can communicate and settle every dispute about concepts, you have a common basis. You are on the object level because that's what is communicable. And it is communicable even if two different persons have different concrete representations of what they have in mind about what they are talking about.
Being independent of foundations, however, is not really a feature only of mathematics. It is a feature that you find in a lot of human knowledge, because one could say that what was found in the 20th century, where basically people found that it was not possible to build the whole enterprise of mathematics on a single foundation, but different possible foundations exist, which is basically a relativistic kind of outcome, had happened before in philosophy. Because basically after Hegel, no philosopher ever tried again to build the whole enterprise of knowledge on a single organized foundation.
Yes.
Which in Hegel too meant it to be formal, although his notion of formal was different from the one of Frege or Hilbert. So in some sense, mathematics retraced what had already happened with the general philosophy approximately 1 century earlier. So I would say that this independence of foundations is probably a character of human knowledge rather than a feature of mathematics alone.
Yes, it's much more general. My talk was about the communication of mathematics, but of course much of this is more general. The way we understand each other on a human level is also based on the same way of meta discussions about what happened to figure out what should have happened, and then there is agreement and harmony again, where before was conflict. And so a lot of this stuff is much more general.
We had engineering without foundations, but a lot of things fell down.
Okay, so thanks, Arnold. So I have some half-baked slides to start us off, but I don't need to go through them. So let me just quickly kind of survey the topics that I'd like to see discussed. Actually, some of these are related to the points that Arnold is making and the discussion that we've just had. So, clearly part of what we need to support our work is formal language, and the choices we make in our language actually affect how well we communicate with others, how well people are able to use the tools that are put in front of them, and how effectively we can automate what's presented to us and by way of formulas and formalizations. So we've already seen a number of language choices that have been made, and some of these have been affected by foundational choices as well. So the choice, for example, of simply typed higher order logic is based mostly on the tradition going back to Russell and Whitehead of type foundations, as well as the ability to actually formalize a great deal of mathematics within this very simple framework. The choice of model of type theory, again, it goes back to this Brouwer-Heiting-Kolmogorov view of the semantics of constructive proofs as embedded within a type theory that exploits the Curry-Howard isomorphism. And again, that, many systems are based on this, and they've, I think, done a remarkable job of actually formalizing a great deal of mathematics. So the question I think we can boil down to, the first question is, is anything erasable here? So, we can, which should I know?
The rise is down here.
Oh,
Yeah, but if you grab it, if you just pull it up, you can grab it.
Oh, there, okay. Actually, I could just reuse the sentences Arnold has, but let me create a few new ones. So the first question is what are we trying to communicate? So, I think this is really a question that has many layers of interpretation. One is, of course, we're trying to communicate mathematics, we're trying to communicate formulas, proofs, counterexamples, models.
Let me get a clarification. Is it you're trying to communicate among human beings or machines?
That's the next question,
or
actually,
machines
who are we
and
trying to
machines?
communicate to? But that's, even if you're just talking to yourself, what would you be communicating is the question there. And who are we communicating with? So, but in this case, one of the things that you might care about is, we're just trying to get to QED, it doesn't matter how. We're just trying to say that this is a theorem, or we failed to prove a theorem, and this is the reason that we failed to prove a theorem. Another is that you might say, these are precisely the axioms I use. So the other thing you might be trying to communicate is that, forget about the QED. This is the, I'm trying to communicate a proof technique to you. I'm trying to actually, tell you how to do these kinds of theorems. I'm trying to give you machinery that you can use, either machinery in the form of actual automation, or machinery that you can use in a heuristic sense to actually do other similar examples. In this case, the communication it does become important. If you're trying to communicate with, as Arnold said, with a graduate student or with a fellow mathematician, that's a level of communication that's different from trying to communicate with, say, a beginning student or a high school student, and that's a different level of communication from trying to communicate with an interactive theorem prover, with a SAT solver, with a SMT solver, with a computer algebra system, and so on. So these are all different targets for your communication. Then the other thing is that in terms of the language itself, you want the language to not just communicate with other human beings. When human beings use it, they should derive some benefit from using a precise language in terms of where is Macarius, for example. You might have a structure editor associated with that. Maybe you're able to find errors more effectively using the automation. So in some ways, trying to find in the language a synergy between automation and effectiveness of communication, the effectiveness with which you can access the automation and so on. So the language itself should strike a balance. I mean, you know, otherwise we just say, fine, natural language is great. We've been using it for a long time. You know, okay, sprinkle a few formulas into natural language here and there. And the problem, you know, that you end up with is that it's great for some human beings. They're able to fill the gaps in there, but it's lousy for automation because the automation sees all these ambiguities in the natural language, and it doesn't have the same system of constraints to resolve these ambiguities. I mean, humans actually, when they communicate, they carry a lot more context than we can currently.
Well, the automation is lousy.
Oh, the automation is lousy. Yeah, that's right. I mean, sometimes finding the ambiguity is what the automation is good for. Okay, that's it's something where the human may have not noticed that there is a specific ambiguity there, and the automation actually finds it. So that's another question there. And in particular, with this, there's basically, when you're talking with machines, that there's a different level of communication. There's a SAT solver, an SMT solver, kind of interactive improver. And a human reader maybe. And I'm curious about people's experiences. I mean, the first was, of course, with respect to Cesare, being here, and with respect to SMT solving and so on. So, for SAT solving, there is the Dimax format. Okay, so it represents the Boolean aspect of the formula. But there are a lot of problems SAT solvers can solve whose initial encoding is not in Boolean form. And so you can deal with finite data types. You can deal with arrays over finite arrays over finite data types. So there's actually a lot of data types that can be handled. And there are languages like Alloy, for instance, which actually do the reduction to they're able to actually do the reduction. Actually, one of my former colleagues wrote one called Smitten. I don't know if people heard of SMTEN, which would take a front end and actually translate it, do the encoding for you in terms of SAT and SMT. That way, you were relieved of the burden. The counterexamples came back to you in the form that you expected, not in some encoded format. So that kind of front end is actually important, and I don't know how many people have wanted that. I mean, I think SMT-Lib2 is great because it's a kind of uniform layer that all the SMT solvers can speak. But maybe there's things that you really want above that can encode to SAT or SMT that would be useful as well.
Yes, I mean this is an issue that comes up all the time, obviously. And the goal of SMT was to provide a low-level language so that you could communicate between tools at the level of the SMT solver. But of course, you need to bridge the gap between the original application. And I'm not aware of general translation tools, also because the translation often is application specific. But there is a lot of effort that is gone in individual groups, for instance, in the LOA team, in coming up with good translations. Often the translation solves, it's solving half of the problem.
That's right. In fact, the translations actually take care of things like symmetry breaking and so on. They recognize certain properties.
It's important to stress that LOA is actually a high-order language.
Right.
And it goes all the way to SAT. And the reason it gets a lot of power in terms of being practical is because this translation step, for instance, puts a lot of effort in breaking symmetries and other things. When you do it in more powerful language, such as, for instance, the SMT language, the issue comes up anyway. And there are symmetries that are for certain levels too. So if you, for instance, we experience this ourselves in trying to build model finders at the SMT level, you still have to deal with issues of translations. I don't know that this is something that can be standardized one, and where we can go beyond basically sharing experiences. but there are many, many issues. For instance, if you go from standard high order logics to basic first order logics, you have to monomorphize, for instance, because the low level doesn't support.
Actually, this is again a source of contention. The Y3 folks have been strenuous in arguing for putting some polymorphism at the level of.
Oh, yes.
Well,
So this is where I'm
you
going.
don't have to monomorphize, right? Like
Sorry?
you can translate in a way that the polymorphism is taken over by the first logic theorem. Like it's
Yeah,
not-
but it's quite complicated. I mean,
Well,
that's why Paskevich and Sonder did it, but if you have interpreted.
well, like for Cesare, it's the only option basically.
The point is,
You have dependent types, but like, you don't monomorphize.
yes, but the point is, whether you I was given that as an example, where you monomorphize or use other tricks, the translation really is important. A lot of the performance that you get, both negative or positive, comes from the way you've done the translation. You'll know that we have a standard, level of expertise now. People have different experiences in that.
Is the issue clear to everyone what this monomorphic versus polymorphic translation issue is? So you can take a problem and say that I'm just treating the for all t as some kind of a Skolem type versus something that you can actually instantiate on the fly as you're doing the inference. So that's a richer level. So that's the kind of polymorphism that the Y3 folks want. And
Well,
I think
there is
Pointogo supports that.
There is a trend in SMT in moving, well, in some solvers at least, that trying to move closer to these applications. And for instance, there are solvers already, like Altergo, that directly support these more complex features, such as type quantifications and axioms. Right? So there, you don't actually need to monomorphize, it's done by the solver. We're going to introduce that in CDC4 next. In fact, there's also trends of trying to automate as much as possible, even in, with the goal of supporting more powerful logic, such as high order logic. For instance, there's a lot of high order reasoning that you could do automatically that is not intrinsically high order. So in principle could be done by solving. So the reason I'm mentioning is that because the bar is constantly moving, also the translation itself cannot be standardized. If you have a solver that supports directly the features that, some features that you have, it's a lot better, right, versus having a solver that doesn't. And again, the Hammer people have a lot of experience in this, and they spend an insane amount of time trying to address all the levels, customized translations for all the kind of
So
levels that it's.
let's switch to that topic then. Jasmine, tell us some of the
Right.
horror stories.
Horror
When you
stories.
come in front and tell us the horror stories.
Well, I think, first
You
of all.
want to stand here?
Oh, no, there's.
You'll be on camera.
Yeah. No.
Go. No, I mean,
Okay. Yes, I'm very unprepared. Hello. So my experience is I've been looking at counterexample generation and proving. So when you say hammer, actually, from some of the examples, I was also thinking of tools like alloy, nitpick, and so on. So my nitpick is based on CADCA, the backend of alloy. So just for simplicity, say that it's based on alloy. And also Nunchaku, the successor. And indeed, what happens is we have like a richer language in proof assistant, and proof assistants are very general tools used by many people for various purposes. So in some sense, we're quite general by going there. So the first order people are wondering sometimes, okay, what's the next feature that's necessary? And because they tend to look downwards to SAT and so on, they don't always know. It's my impression, I don't mean this as criticism, don't always know what happens upstairs. But for us, it's the opposite. We look down from a richer logic with the variety of users, and then we look at various idioms, the various things that people use. Sometimes these idioms are supported by the proof assistant, so things like data types, co-data types, quotient types, inductive predicates, co-inductive predicates, recursive functions, co-recursive functions, and so on are things that, like quotient types and nominal data types, binders, and so on. These are things that always pop up, at least in O world. Arithmetic as well, but arithmetic not necessarily on reals and on integers, but also we have these algebraic structures, so lots of lemmas about arithmetic in Isabelle and also probably in Lean is not on the two main types that are supported by simply solvers, but rather on abstract, on type classes typically, which can be instantiated by various types that have the properties later. So this kind of world we evaluate, we live in, and then I try typically to find translations that are as lightweight as possible, that preserve soundness, that are ideally complete, but efficiency is extremely important. It might be more important than soundness, almost. Than 100% soundness. So the first sledgehammer, for many years was not even sound. It was just a reconstruction that made it sound. Reconstruction or proof checking translates unsoundness into incompleteness, right? So it's an interesting mechanism in that respect. But yeah, so for I already mentioned some of this in my talk the other day. For model finding, the main killer is the for-all quantifier in a positive context, and we're trying to recognize various idioms where we think, oh, actually we can find a counterexample by only evaluating finding many things if we rewrite the problem like this. So we use some idioms that were developed for alloy. So there was a paper by Kunchak and Jackson about encoding data types and generalize it to codata types, generalize it to lots of much richer set of data types and codata types like we have in Isabelle. But yeah, thank you for yeah, go ahead. I don't know what to say.
Well, I gather that Sledgehammer is now by far the main client of resolution theorem provers, which I hope is influencing their design. Now, what about Nitpick? Is it one of the main clients of COD, do you think?
Yeah, less so. So, COD has maybe, I don't know, maybe there are 20 or so tools based on it, at least judging, and Nitpick is one of them, it's listed on the webpage. It's maybe less influential because we're starting with these very general theories, and as I said, Nitpick is very useful when it works. When you're in a fragment where it works, but that fragment is still too small. It's just the way it is. So I think because we start with higher order logic with all these quantifiers and so on, we're not in ideal fragment, so to speak, and translations are still not entirely there. And I think they will never be. You always have some evil quantifiers you don't know what to do about.
So to what extent can these issues be fixed in translation versus, you want to actually change the theorem prover?
Right. And this is a very good question. I'm always asking myself that. So in 2013, 2011, I had a paper at TACAS about how to encode types. And I was really proud of our scheme, and we have a 50-page journal version of that now and so on. But most of it in practice is obsoleted now because I was encoding polymorphic types in very clever fashion, but it turns out that monomorphization is usually the way to go. And now most provers support at least monomorphic types. So that research is interesting and still used a little bit in Sledgehammer, but in practice, monomorphization, which is very simple. It's heuristic monomorphization. You do a certain number of iterations. At some point, you say, okay, I've got enough formulas, I stop. That happens to work pretty well in kind of hammer scenario. So you don't need the other translations. So then I thought, okay, I should not work too much on translations. It's actually often easier to do things directly in provers. Then I started working with developers of provers, like Spass people who had paper 2012, added various features to the prover, like designed for proof assistance, and then worked also with CVC4 people, and I might be forgetting, now with Verity people. So now I believe more into adding features directly in the automatic theorem provers. But there will come a point where people in automatic provers will say, whoa, we have too many features, we need to kick some out. Just pushing features into the automatic systems. I understand. I think we're still at a point where it makes sense, but there's probably going to be a pushback, and we'll find out which features actually belong in automatic prover and which ones are better left as an encoding.
So if like, for example, you become the main client of these theorem provers,
Yeah.
then, the theorem provers start to.
Yeah, they do start listening to me.
Optimize,
So Vampire has an Isabelle option now that turns it into a mode where it's optimized against Isabelle benchmarks and so on. So I mean, I've noticed in the past few years that
Yeah,
I
we've
have
done-
much more leverage with those guys.
We've done the
Put
same
it this way.
We've done the same with CDC4, like put a lot of effort in making him happy. Because it was an important application for us. But it's interesting that it becomes now not just a technical issue, but also a social one, right? Meaning being able to talk with other groups and convince them that they should move in one direction as opposed to another. And
Oh yeah, it's a
Usmani's
huge
been doing
social.
a lot of that, right?
It's a huge
Right.
social
I don't know if you wanna
experiment.
comment
Yeah.
on that as well.
Yeah, so I mean, in my case, so I have this project now, and it's about taking existing first order. It's called Matryoshka. It's about taking existing first order provers and extending to higher order, and it's combination of soft power, money, and everything, right? Because I don't want to write a new first order or higher order prover from scratch. I want to start with what already exists. So I have to find people. And in the project, so I'm working with Pascal Fontaine, and I mean, I left 1/3 of the grant in his hands, and he's very happy, and this was a direction he wanted to go into anyway, so, I mean, it was actually his idea. At some point it came to me, he's like, we should extend Verity to go high order, so I mean, I just leveraged that, got money, and now that's what he's working on. But also the CVC4 guys seem to be interested, so I mean, in the project, like Andy Reynolds, and of course, Cesare. So yeah, I mean, I see this at this point as a very social, political thing, like trying to find the right people who will let us work directly on their repositories and will contribute themselves and so on. I mean, that's the hardest part in some sense.
But in this slide, perhaps we should erase the word interactive from the black box, because really interactivity and automation are a continuum, both of them. I mean,
Yes.
also this notion that you have of automatic theorem prover, why automatic and not automated? I mean, there is interaction there too, just like there is automation in what is called interactive theorem prover here. So both measures, we can see them on a continuum.
Yes, they are continuum for sure, and you see it with Otter. I mean, like Otter will find a proof, will give you some hints, and then you can reuse them to reflate things. I mean, this is what Sledgehammer does. At some point we use different names for the same things.
I very much prefer the term automated theorem proving for that reason, because somehow
Then it's both.
it brings them together as a single subject.
Exactly.
But I like automatic when you mean the opposite of interactive.
Well, for sure.
I mean, if you
That's
talk about
English.
At the same time, I mean, I wouldn't say that they're all exactly the same thing. I think, I mean, there are some things that work well in automatic, and if you apply the same thing to an inductive prover, I mean, there are some new challenges from the fact that, you have some theories and you maintain them over time and so on. So, and interactive often are just too weak to be used as a black box and so on. So I mean, I think how to say, we're not going to see, at least I don't believe we're going to see systems that are really great at both. But I mean, I might be wrong. I know Lean aims at that, but I mean, so with the evaluator, there has to be some compromises about how powerful you make it and how predictable you make it, and it's hard to make, how to say, both sides.
So there was this
happy.
pushback, at least from Tim Gowers, in that he was saying two things. One is that he doesn't want too much automation. He wants it to be where the person presenting the proof is given enough detail that it's almost a deterministic process to complete.
Right.
Versus something where the automation goes off and actually finds maybe it finds a great proof, but typically it might find something that isn't that. I mean, he doesn't even think, for example, McEwen's proof of the Robbins conjecture is humanly accessible.
Well, I think there's another axis, which is the lemma you're proving right now. Is it a boring, or theorem? Is it boring background stuff, or is it the stuff you're working on and that really interests you? And I think you want a lot of automation for boring background stuff. And I think even he would like that. I mean, he's thinking about his own proof steps that are interesting to him, and then he wants to go in big level of
Right,
detail.
and it's not necessarily the case that a boring step is actually easily provable. Whereby easy, you could say Google search, right? It might be that.
Right, might be hard for a computer.
It might
I
still
mean,
be hard, and this is where automation.
I mean,
yeah. So I partly agree, but partly disagree. I mean, it really depends on what you're doing. And Tom Hales was saying, you want to do something as simple as have a half circle and have a line. You want to say the line meets the half circle in exactly one point, and so on. And you'd like to just type that and somehow, and then press a hammer, and then it's proved, right? Don't want to go into. And I see this is one of my criticisms of Misar. Misar encodes the philosophy in language. It says you have to do everything by small steps. It's like it doesn't trust its users to choose.
I wouldn't say that. Well, like the Misar step is actually reasonably powerful. Like the Misar by automation.
Yeah.
Like it's really like it hasn't been invented by Tim Garris. It's been invented by Martin Davis in the 60s. When he wrote this paper about what it means to be an obvious stem. And the Misar people really put a lot of effort into tuning it, not to be too powerful and not to be.
Yeah, but it encodes
simple.
an exact philosophy of what it means to be too powerful. So they would be, say, against a hammer that in one step does 5 Misar steps. And I would prefer to leave that to the users. They decide themselves in which parts they want.
Actually, I want to segue that into the last part of the discussion, actually, which is this
Okay.
declarative versus tactical proof styles. So I think there are people here who have experience with both. And my contention has always been that you want to discover the proof in this tactical style and then capture it in a declarative style for further maintenance. But I think there are people who do things differently from that. So is there a? I mean, does anyone have any opinion on this? And because both of these have been used quite heavily. So Jeremy, yeah.
I mean, in Lean, as in Isabel, we sort of have a framework where we can sort of do it both ways. I mean, you can start writing a proof term, and start writing tactics. In the tactics, you can present a proof term. So you don't have to choose one or the other. You can have both. I think one thing we're learning is that, I mean,
No, but can you take a tactically developed proof and then declarativize it
automatically or by hand, where you?
automatically? Yeah.
Well, you can certainly print out the proof term.
No, the proof term isn't the same as the declarative thing, right? And the declarative thing assumes that you have a few simple.
Sort of.
I
So
mean, it may not be.
You annotate, if you take the proof term, stick in all type annotations, and then you have a declarative proof.
Yeah, that's not what these are, is, right?
But I mean, the other thing that we.
That's the ultimate declarative proof is exactly that. And then you have declarative proofs where you decide, okay, I'll chop off the leaves and at some point I'll drop any justification whatsoever and say, and insult the reader and say,
Exactly.
this is obvious, you silly.
So that's what I'm thinking of, that you just kind of signpost the proof, with the gaps being filled by some standards.
So what you can do is you can put structuring elements into tactic proofs. So now we can say, assume, have, show in tactic proofs that make them look a lot like the proof terms. And so there really isn't a sharp distinction between the two modes.
Although, a tactical thing you can extend with new tactics, whereas a declarative thing presumably is a fixed language.
But it can't be automated because the point of a structured proof is to communicate to a human, and I don't expect to see convincing automation that will produce a document. Now, you can make a thing that syntactically is a structured proof, and which is much more readable than a tactic proof, but it's not really a masterpiece of communication to a human being.
So you think you should hand process it from
Yeah, at some point, at least massage it.
Deepak?
Yeah, so let me make a comment. It's not my comment, it is a comment coming from Bob Beroff and Michael Kinnan, because they essentially, very much like what McKeown was doing with Robin's problem, they have done numerous proofs, and I think probably Joseph knows more about that than I do. But what they end up having is essentially automatic proofs using prover 9, which are hundreds of thousands of lines. And then they have difficulty in publishing that because no journal is willing to take their proof. And they have tried to struggle and figure out how to present them, but on many problems, they don't yet have any way of presenting it. Like McKeown succeeded in presenting Robin's, the proof of Robin's theorem, essentially of conjecture, basically nicely afterwards. But obviously, original proof that he had was, probably hundreds of thousands of lines of order steps or whatever extension of the order step with AC unification and all that. So that's another issue which people like Tinelli and Beroff face, and they don't know how to communicate to other mathematicians.
No, but I think this is a good thing in that I think, we need complementary intelligence to discover the proofs, and, some of these things, humans may not even have thought of doing some of those unifications or instantiations, and perhaps, that's the secret to discovering those proofs. But I think, it's possible then to kind of post-process these proofs and come up with something more intelligent.
It's not clear.
I think
Oh,
That's
well,
what is not clear.
they are
Because
searching
no
for
proof.
the technology for the past 10 years.
Yeah,
And they
it's not clear.
I mean, we have tried something, just managed something reasonable, etc. But I don't think this is a solved problem. It's a hard AI problem. Like sometimes, like George 4-color theorem, like if you solve it for 4-color theorem, you're a famous, right? Because nobody did it.
Yeah, Arnold. It'd be great. Wait, Arnold,
What I would like to see as a mathematician is that if something is automatically proved, I don't get the proof, but I get sort of the kind of proof sketch, which gives 3 or 4 or maybe 10, but not 100
Actually, that was another thing that came up, yeah.
main pieces of information and some summary of how to go from one.
I mean, you can browse, you can
Yes,
have a
and
proof
then you
browser
can-
that
and
lets
then
you
you want
open
to-
But see, in their case, that's also very difficult. They cannot do that. And they are able to prove open problems, in lattice theory and other related things, but they just cannot come up with a high-level sketch.
The idea is something like this: you have zero complicated proof with many lines of arguments, and then there are pieces which that's what happens in a mathematical proof. You have lots of stuff, and then you have a few statements, and everything later depends only on these few statements. So you want to see these, and you want to see some, and this must be detectable automatically because it's a graph theoretical problem.
But I think that this is what Larry was saying, that like you can like the very simple technology that we have now is to say these are, let's say, the most frequently used lemmas in the proof, and maybe like various people did various things for it. But these algebras, they are looking for something which they call a structural formulation of the proof, which is like a totally different reformulation of the proof from the rewriting way, how it was found, to the way they are thinking about it.
And this is slightly different. These statements might be used only once or twice, and there might be the same lemma might be used 100 times a year. This thing is just if you have if there's the logical structure of your proof written as a graph, as a directed acyclic graph, you should be able to find these things.
We do that, but it's not what they want.
Okay.
Well, it's been done in a trans system, and then you can zoom in. I mean, it was quite nice, but again, different.
Can I make one more comment?
Just 1 second, yeah, so if it's about this, you can.
No, it's
then
slightly
if it's
different.
not,
Somebody
then-
show
Then,
representation.
I'm getting hungry, so Maria Paula, then Larry, then Deepak, and we'll finish.
So as far as the Robin's conjecture, the Robin's theorem is concerned, people should remember that there isn't only the paper that McKeown McCune wrote to present the proof by EQP, the automated prover. But there was also another paper by Godin
Right.
that consisted in turning the proof into something understandable to humans, into a more classical human algebraic proof. But it was based on the machine proof. So there are these two papers to check. And as for the difficulty of communicating the proofs, I agree. For example, McCune worked for many years with the mathematicians, writing two authors' papers, because he was providing the automated part and the mathematician was providing the rest. Now I don't remember all the names, but if one looks at the bibliography, but Manaman, exactly, thank you. So they worked together on those lattices and ortholattices problem. So it was a team effort, putting together complementary expertises.
Okay, I wonder whether the problem in publishing some of those results, if they're like typical of the problems published in the AIR newsletter, is a lot of them, although open questions, are highly technical questions that I suspect nobody cares about, like, do the following three very strange looking axioms, are they complete for propositional logic? And then if you find a 10,000 line proof of that.
I wouldn't say so. So it's really like, for example, David Stanowski, like 7 years ago, got a proof of an open conjecture in the quasi-group theory, which he said would be the result of the year. And he got 20,000 steps from Waldmeister, and they told him, this is a good result, but you didn't give us a proof. So the community isn't big. It's not like Fermat's theorem or whatever, but the community is there and the publishing means are there, but they do not consider this to be a proof which has any value for them, basically.
Why do you call them quasi-groups when the community would call them Latin squares?
Well, they call them
they
small
call them Latin
quasi-groups
squares
and
also.
loops, most of the time.
Well,
Okay, so the other thing I want to mention is the whole issue of representation. For example, in the 80s, Professor Wu Wenzhun started essentially an algebraic way of doing theorem proving in Euclidean geometry, which was picked up by Cho and Gao and myself later on. The proofs there have no relationship with the proof a human being will do. And I think I even conjecture that it's almost impossible from those proofs to get a proof that is human understandable.
So, but later on, Cho and Gao switched to this
Yeah,
area.
no, but that's different, for example. But the proof, those methods that we developed, they were very, very fast. They could prove things very, very easily. But the proof that was being generated was incomprehensible.
Yeah, I personally think, there's plenty of value in knowing that, there is a proof. I think that, this can create a problem in that if a human mathematician does come up with a nicer, more readable proof, who gets priority on this? But I think, knowing that something is a theorem at least saves you the trouble of going off and searching for counterexamples. I think the, fly-spec proof, you can, look for something that the Kepler conjecture proof, it's still an open problem maybe to find a single page proof of it or something like that, or a visual proof of it. But knowing that it's a theorem is, I think, a game changer for a lot of these things. You don't have to search for counterexamples or search for other arrangements and things like that anymore. So, actually, you can switch the game to maybe finding a mistake in this 100,000 line proof, and I think there's a huge amount of work to be done in that. I think that, in these languages we're creating layers of abstraction where clearly you can communicate to humans through these layers of abstraction, through the shared abstraction. You can communicate to automation through the shared abstraction. You can preserve some of the content and the meaning of the source formulas in the translation if you have a well-chosen language. And so I think there are research issues here that are going to be keeping not just the people in this room, but elsewhere busy for a very long time. So I'm happy that there was so much discussion around these issues because these topics do matter to me a lot. So. So let's get some lunch. Thanks a lot. Yeah. So this afternoon, Jeremy will be doing a session on big proof in education. 3:30.